All right, so chapter 13, we're talking about gases and gas laws. And remember, we have a number of gas laws that we talked about. We had Boyle's law, P1 V1 equals P2 V2. We had Charles' law, V1 T1 equals V2 T2. We had Guy Lusik's law there, P1 T1 equals P2 T2. First one here is at constant temp. That's at constant pressure. And this is at constant volume here. We also had Avogadro, V1 N1 equals V2 N2. Avogadros. And that's at constant pressure and temp. We also had obviously the ideal gas law, PV equals nRT, which again is the most restrictive in terms of units. That should be atmospheres, that should be liters, that should be moles. Remember, temperature here is Kelvin. Pretty much temperature in all gas laws do you need to be in Kelvin always. And R is a gas constant, which is a value you always have, but very rarely ever given to you. So they just think you know it. So you got to make sure you know it there. And we also talked about STP, which is standard temperature and pressure. That is a temperature of 273.15 Kelvin and a pressure of 1 atmosphere. Remember, there is a relationship at STP that 1 mole of any gas there will equal 22.414 liters at STP. So remember to use this conversion. You do need to be at SCP. If it's not at SCP, you should not use that conversion. If you don't even want to worry about that conversion, you can always use the ideal gas law in every situation, SCP, non-SCP conditions. Then we had our combined gas law, which is our P1 V1 T1 equals P2 V2 T2, and that is our combined gas law. Remember that a version of the combined gas law is a really good one to remember. As we talked about, if you did the P1 V1 N1, T1 is equal to P2 V2 N2 T2. If you remember this one here, and essentially just scratch out whatever is constant, whatever is not given to you, you'll be left with pretty much all the other gas laws that you would need. So again, as we talked about last time, thank you. I would invest your time there in remembering this one and how to scratch out anything that's not given to you or you don't need. And ideal gas law is a good one to know as well. Any questions on any of those there? Yeah. And again, a reminder how you do that. For example, if there was no mention of moles or temperature, are they held constant? All you have to do is just scratch them out on both sides, and now you have your Boyle's law and stuff like that. So again, that is basically how you do it. Next thing we're going to talk about is actually stoichiometry involving gases, and we could do stoichiometry problems with gases. The good news is it's really the same steps as you do in a basic stoichiometry problem. The only difference is somewhere along the way you're going to use a gas law pretty much. So you basically will still balance your equation. You'll still convert to moles. Remember as well, in any stoichiometry problem, you could have a limiting reagent situation, and you could also have that with gases as well. So again, if it is a limiting reagent problem, you do need to do that middle step here. If not, obviously you could skip it, and then you would do your actual stoichiometry here, mole to mole. And mole to some other unit. So where do you sort of incorporate a gas law? I would say probably in most cases it's going to be the ideal gas law or maybe the combined gas law, but in most cases, probably the ideal gas law is what you're going to use. If you use it up front, probably you would solve for using our PV equals nRT. You probably would solve for moles. So if you kind of use it up front, probably moles is what you would be solving for. Then you would continue on with the calculation like normal. And probably most commonly, though, at the end of the calculation, you would maybe use it to solve for the volume of gas you collected. That's usually very, very common sort of thing. So I would say those are probably the two common places within a stoichiometry problem that you would have to sort of insert a gas law into, and usually, again, moles early on, and then usually volume there on the back end. Um, you could also use, for example, on the back end, something like the combined gas law, like you maybe did in the lab, the gas lab as well. So that's something that you could do as well. All right, so let's try one here. What is the volume of CO2 that would be produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose are used up in the reaction? So again, just to kind of show you the steps here, we would follow the same normal steps. So we would take our equation that's balanced, so we're good. In this case, we are looking to produce what volume here of the CO2 gas. We know that the gas is at a temperature of 37 degrees Celsius. We also know it's at a pressure of 1 atmosphere. So we have all that sort of gas information. So usually what you would want to think about is probably the ideal gas law. So if we think about the ideal gas law, PV equals nRT, and we think about it in terms of the CO2, we have a temperature. We always have R. We do have a pressure. We are looking for the volume. So really the one thing we're sort of missing here to allow us to use the ideal gas law to solve for the volume of CO2 is actually the moles of CO2. And in this case, this is where the stoichiometry will come into play. We could actually use the other piece of information given to us, which was we are starting with 5.60 grams of our glucose. So we could do a stoichiometry sort of calculation to get to the moles of the CO2. Once we have the moles of the CO2, we'll have everything we need to basically use the ideal gas law. So we'll start it just like normal. We take our equation as balanced. The next thing we want to do is calculate the molar mass so we can convert this guy into moles. So again, that would mean you'd go to periodic table, add up all the parts. So we have something like 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens, plus 6 times 16 there for our oxygens. And let's see what we get here. 6 times 12.01 plus 12 times 1.008 plus 6 times 16. Looks like 180.2 grams per mole. That is going to be our molar mass conversion that we get from the periodic table. And we want the grams on the bottom so that they cancel. And moles here of C6H12O6. The grams are going to cancel each other out. And this is really like it's actually more like our that's our first step. This is our second step here, converting to moles. Now, if we were to stop the calculation right at this point, and if you got a number, which you could get a number if you like, we would have moles of our C6H12O6, but we really don't want moles of that. We do want moles of our CO2. So we would do our third step here, which is our stoichiometry, and we want the relationship between these two guys from the equation. And again, from the coefficients, we could see that for every 1 mole of our C6H12O6, we get 6 moles of CO2. So that would be like our third step here in our stoichiometry problem. 1 mole of C6H12O6 gives us 6 moles of CO2. That's going to get rid of those guys. And that will get me 5.6 times 6 divided by 180.2. Looks like we'll call it 1865 maybe. So 0.1865 moles of CO2. Any questions up to there? So really just a basic stoichiometry problem, balance the equation, convert to moles, mole to mole relationship. Now that we have the moles of our CO2, we can now use our ideal gas law really in the fourth step here. And in this case, we're going to solve for volume, which is nRT divided by P. We do need to do a few conversions, or at least one conversion I see. We do need to take our temperature from 37 degrees to Kelvin, right? So we need to add that. And that's going to get us here 37 plus 273.15. Remember that if you're using a gas law and you have temperature, it should really be a no-brainer. You should always go Kelvin, yeah? So it should almost be like the first thing you do. Our pressure here is 1 atmosphere, which is good, so that's okay. Remember, we always have R, which is that 0.08206 number. And that's really all we need at this point. So putting in our numbers, we end up with 0.1865 moles of CO2 times our R, which is our gas constant, 0.08206 liters, atmosphere, Kelvin, mole. Our temperature converted to Kelvin, so everything properly cancels, all divided by our pressure of 1 atmosphere. The moles will cancel, the Kelvin will cancel, atmospheres will cancel. That's going to leave you liters as the only unit left, which is pretty good since that's what we're looking for at volume. So we'll end up with 0.1865 times 0.08206 times our 310.15 divided by 1. Going to give us like 4.75 liters here of CO2. By the way, since CO2 is a product, that would be like a theoretical yield. Remember that a yield has to be a product, right? You can't have a yield that's a reactant. So in this case, since CO2 is a product, that would be technically the theoretical yield. So again, basically the same 4 steps. In this case, we actually use the ideal gas law at the end of the calculation, which I would say is fairly common. But again, you could use it on that second step and get moles if you needed to as well. Any questions on any of those steps there? All right, why don't you try some here then? All right, so consider this reaction here. What volume of hydrogen gas at 27 degrees Celsius and 1.25 atmospheres is required to react with 5.65 grams of phosphorus? Phosphorus is 3097, I think. All right, so give it a go, see what you come up with. Okay, so let's take a look. Again, in this case, we are looking for a volume here of H2. We have some temperature values given to us, 27 degrees. We have a pressure of 1.25, and that's all sort of ideal gas-wise here would be good. So we have temperature, we have pressure, R we always have, which again is a constant. We're looking for the volume. So once again here, we'll have to do a little bit of stoichiometry to get to the moles of our hydrogen here. We could do that because we are given the grams here of phosphorus. So we'll start with our equation, which is balanced. We're going to convert it into moles, what they gave us, the 5.65 grams of P4. We would need to go to the periodic table there, 30.97 times 4, 123.9. And again, if we do that at that point, that's going to give us our moles of P4, which again is our second step. We don't want moles of P4. We do want to get it over to hydrogen gas so that we could use it in the ideal gas law. So here's where the stoichiometry is going to come into play between those two. And from the equation, we can see that for every 1 mole of P4, we got 6 moles of H2. So that is what we will use next. 1 mole of our P4 on the bottom so that they cancel, and 6 moles of H2 up on top. Those are going to cancel. That's going to get us here 5.65 5 times 6 divided by 123.9, 0.2736 moles of H2. That once again is really our missing piece that we needed to use the ideal gas law. In terms of that, we're good to go for our last step, which is in this case using the ideal gas law to solve for volume. Putting in our moles, 0.2736 moles. Gas constant, 0.08206 liters atmosphere. Kelvin and mole has all 4 units. We do always need to convert our temperature into Kelvin. So we do need to add a 273.15 to that. So that's going to give us 27 plus 273.15, 300.15. All going to be divided by, and that's our pressure, not our temperature there. Our pressure on the bottom there, which is 1.25 atmosphere. So that should be our pressure, obviously. Again, here our moles are going to cancel, our Kelvin are going to cancel, atmosphere is going to cancel, leaving us with liters once again as our unit, and we will end up with 5.39 liters here. And this would be of H2 in this case here. Any questions on those steps there? That, by the way, would not be a yield because that is not a product, right? That's a reactant. So again, a yield can only be a product. So basically what that number represents is if you were to do this reaction with 5.65 grams of phosphorus, you would need to toss in there 5.39 liters of H2 gas, basically, to get this reaction to go, basically. Yeah. Any questions on those steps there? All right, let's continue on then. A few more here, I think. Let's make sure. That's the same one. Try this one. All right, so similar to what you did in lab there, magnesium reacts with hydrochloric acid. In this reaction here, what is the volume of hydrogen gas you would produce at STP if you started with 5 grams of magnesium? Magnesium is 2431 here. At STP, so remember when you're given STP, that means the temperature is 273.15 Kelvin. Pressure is 1 atmosphere. So again, it does represent actual numbers here. Same idea, we could use the ideal gas law, PV equals nRT, and we are going to be short some moles here. So we're going to do our stoichiometry to get to our moles of our H2. We could do that with our magnesium, and it's an excess amount of HCl, so that tells you magnesium is actually the limiting reagent, pretty much is what that tells you. And we're going to take our 5 grams here of magnesium. We'll use the molar mass there from the periodic table to convert it into moles. Grams are going to cancel. Again, we don't need moles of magnesium. We really need to get over here to moles of hydrogen. And that in this case is pretty straightforward conversion there. It is a 1-to-1 relationship based off of the equation. So that will then get me my moles of hydrogen, which is basically 5 divided by 2431. 0.2057 moles of hydrogen here. At this point, we now have what we need to go into the ideal gas law. We have our moles, R, T, and P in this case. And that's going to allow us to use, once again here, our V is equal to nRT divided by P. Taking our moles, 0.2057, our gas constant, our temperature of 273.15, all divided by our pressure here of 1 atmosphere. Atmospheres again canceling, Kelvin canceling, moles canceling, leaving us our liters here. And we end up with 4.61 liters of H2. This would be a theoretical yield as that is a product. So that would technically be, if you start with 5 grams of magnesium, that is how much hydrogen gas you should collect, and that would be your theoretical yield. Again, same steps, balance equation, convert to moles, mole to mole relationship, and again, just kind of using the ideal gas law here on the back end of the calculation. Question on any of those steps there? Could I have solved this another way? And the answer is yeah, you could have solved it another way in this particular case. And in this particular case, because this was at STP, we could have used that relationship we talked about, that 1 mole of any gas is 22.414 liters. So what we could have done is, because this is at STP, got our moles of hydrogen and basically just use that conversion there without having to use the ideal gas law. Moles will cancel and it will get you over there as well. So again, this is a place where you could have kind of snuck in that calculation if you wanted to. If you didn't or weren't sure you should use it, as you can see, you could always use the ideal gas law. So it doesn't matter if it's STP conditions, non-STP conditions, it all comes out the same. But once again, this conversion here, only at STP. That's the only time you should use that. So if the temperature, again, is not 273 and the pressure is not 1 atmosphere, you should not use that conversion. You should definitely use the ideal gas law along the way. Any questions on any of those there? Okay. All right. One last one here for good measure. Calcium carbonate reacts with hydrochloric acid to produce carbon dioxide gas. If 35.3 grams of calcium carbonate react with 21.9 grams of HCl, how many liters of carbon dioxide will you produce at 745 millimeters of mercury and 23 degrees Celsius? Let me give you some numbers that might be helpful here. Calcium 4008, carbon 12.01, oxygen 16, hydrogen 1.008, chlorine 3545. I think that's everybody. All right, here you don't have an equation. Okay, let's take a look. So here, obviously, you do not have an equation, so you need to start with that. Remember that when you have things in words, you do want to just get all the proper formulas down first before you worry about balancing. So calcium carbonate, calcium is +2, and carbonate is -2, which means perhaps you get something like that. And you're going to react with hydrochloric acid, which is HCl. This is a double displacement reaction. Basically, we're going to switch partners basically here. And that is going to get you a calcium chloride and actually get you some carbonic acid here when those guys come together. By the way, that carbonic acid will actually go through a decomposition reaction really quickly. And that is actually where the CO2 is going to come from. You're going to actually get your CO2 right there from the decomposition of this guy. So we still need to make sure that it is balanced. So I'm going to put a 2 there, and I think we'll be in business at that point. And again, I'm going to actually get rid of the carbonic acid and put the CO2 and water in the equation so we can see it there. So, oh, water and some CO2 here. All right, so now what we're looking for really is how many volume of this guy at 745 millimeters of mercury and a 23 degrees Celsius temperature. We are starting with, in this particular problem here, some grams, and we have, looks like 35.3 grams of this guy and 21.9 grams of this guy. This is, as you hopefully recognized, a limiting reagent type of problem because we are able to get to the moles of each reactant in this case. So we obviously could use the molar mass there to get to the moles of each. And that again is your key to know that it is a limiting reagent problem. That means you need to take that extra sort of calculation to figure out which one is the limiting reagent. The beginning part's sort of the same. We got a balanced equation. We're going to convert both of our guys into moles. So we got 35.3 grams of CaCO3. Going to the periodic table and adding up the molar mass, 4008 for our calcium, 1201 for our carbon, and 3 times 16 for our oxygen. Looks like it's going to give us 100.1 grams per mole of CaCO3. That's going to get us here. Looks like 0.3527 moles of calcium carbonate. We're going to do the same thing for our other reactant in this case. So we got 21.9 grams of HCl. For our HCl, it's basically add the hydrogen and chlorine together to 3545 plus 1.008, 3646 grams per mole. Again, the grams cancel, and that gives us 0.6007. So remember, this is basically your starting amount of each of your reactants. So one way to figure out the limiting reagents like we've been doing, we basically just going to take one of the reactants and try to figure out how much of the other one we need to use it up. So I'm going to figure out how much HCl I need. So to do that, I'm going to take the starting amount of my calcium carbonate. I'm going to do my mole to mole relationship between the calcium carbonate and the HCl in this case, which is a 1:2 relationship. 1 mole of CaCO3 gives you 2 moles of HCl. Those guys are going to cancel. That's going to get me here 0.3527 times 2. 0.7054 moles of HCl is needed. Remember, this is the point where you bring it up here and kind of compare. I need 0.7 moles. I have only 0.6 moles to start with. I do not have enough. And because I do not have enough, that means that the HCl is our limiting reagent and our other guys actually are excess reagent. Any questions on that one there? Now, in this particular case, we want to then figure out how much product we're going to produce based off of the limiting reagent always. So we'll use our starting amount of our limiting reagent here to do the rest of the calculation here to get our moles. So now that we did that there, we have 0.6007 moles of HCl. Remember, you want to start with the starting amount. We'll do our mole-to-mole relationship between the HCl and our CO2, and it is a 2-to-1 relationship between those two. So 2 moles of HCl, 1 mole of CO2. That's going to get us here 0.6007 times divided by 2, 0.3004 moles of CO2. That is what we need to go into our ideal gas law here. So again, our volume is going to be nRT divided by P. We have a couple of conversions we need to do and before we could go in there. Our temperature, like normal, needs to have our 273 added to it. And that's going to get us here. Twenty-three. 296.15. Also, our units for pressure is no good for the ideal gas law. It needs to be in atmospheres, right? So we'll go 745 millimeters of mercury divided by 760 in an atmosphere. 0.9802 atmospheres, not moles. All right, now that I have everything, we could go into here. Our volume is going to equal our moles, which was 0.3004. Our gas constant, our temperature squeezed into the corner here of 296.15 Kelvin divided by our pressure 0.9802 atmospheres. Again, everything's going to cancel out except for our volume here. And that's going to get us 0.3004 times 0.08206 times our squeezed in temperature there, 296.15 divided by 0.9802. Going to give us something like 7.45 liters here of our CO2, which would be a theoretical yield in this case. Any questions on that one? Yeah. Here. That's the conversion factor between so that's the conversion factor. There's 1 ATM is equal to 760 millimeters of mercury or 760 torr. So that 760 is really the conversion factor go between those. And a reminder that millimeter of mercury, right, is basically equal to a torr. It's a one-to-one conversion between those two. So it's basically the same number, just change the units. We had to convert it, but that 760 is what we convert between those three. Other questions? Yeah. Questions on stoichiometry. So again, as we see, I could have a basic stoichiometry problem with gases. You could also have a limiting reagent type problem. So you just got to keep an eye out of that. I would say probably a majority of it would probably be a basic stoichiometry problem, but a limiting reagent one could pop in there somewhere along the way. Next thing we're going to talk about is actually Dalton's law of partial pressures, which sounds very difficult, but it's not too bad of an idea. This has a really long name, I suppose. So the idea behind this is pretty much this. If we have a container that pretty much only has one type of gas molecule in there is flying around, basically all of the pressure of this container, the total pressure, is basically a result of just that get one gas molecule or one type of gas molecule basically flying around. Now, if we had a mixture of gases, which is very common as well, we have different gases together, A, B, and C there. As those guys are flying around and causing collisions, the total pressure of that mixture of gases is actually the pressure of A gas plus the pressure of B gas plus the pressure of the C gas that's basically flying around. These guys over here are what are referred to as partial pressures because when you add them together, you get the total pressure. So they each contribute partially to the total pressure of that mixture. Now, one of the nice things about the idea of an ideal gas is one of the things we talked about earlier, that what makes something an ideal gas, or one of the things that makes something an ideal gas, is the idea that there is no attraction are repulsion type forces between gas molecules. So even though, for example, here on the right-hand side, I have gas molecule A, B, and C, different gas molecules flying around in the same container, because in an ideal situation, there's really no interaction between any of those different gas molecules. We could almost think of each of those gas molecules as being in there by themselves. And what that allows us to do is basically to figure out the pressure for each of those gases. We could just simply, in a lot of cases, use the ideal gas law. And what we would be doing is solving for P, for example, for A, and that would be nRT over V. We could also do it for B, and that would be nRT over V. And we could also do it for C, which would be nRT over V. So we can individually solve for pressure using the ideal gas law. One of the nice things as well is because this container is in the same room, the temperature and the volume will be the same for all the gases that are in that particular mixture. So they'll all be the same. That means that if you just think about it, the temperature and the volume is going to be the same. R is a constant. It means that essentially the only thing that you have to usually calculate is how many moles of each gas that you have. And then you basically just plug it into the ideal gas laws individually. If you have two gases, you do it individually for each one separately. If you have three, you do it 3 times. You have 4, you do it 4 times. At the end, you'll get pressure for all of them. All you have to do is add them together, and you'll have the total pressure of that mixture of gases. Any questions on that there? So again, as you can see here, the volume and temperature is going to be the same for all the gases. So if we have this gas and we put it together with this gas, even though, again, they're all flying around together, the part of that ideal gas is there's going to be no interaction, and there'll be hopefully no problem that's going on with it. We're going to skip this calculation, I think. No, we're not. So again, just the ideal gas law there. So the reason why we ignore that again in an ideal gas situation is there is no attractive forces or repulsion forces. And that's not always the case, but it probably will be always the case in this class. When you go to 1A, it will not be the case. You'll learn about real gases, or sometimes they're referred to as non-ideal gases. And in a non-ideal gas situation, you do actually have to take into account the volume of the gas itself and also the interaction between the different gas molecules. And why would you have to do that in a sort of non-ideal situation? Let's just say you had this gas molecule that was heading towards that wall to collide. If there was sort of an attractive force between those two gas molecules, it may drag that gas molecule back a little bit, and it may not hit the wall as hard, and it may not hit the wall as often, and it may cause a difference in the pressure that you would associate under a non-ideal situation. Just like if they were repulsed by each other, this guy would fling away from that guy as fast as he could, and also could cause a variation in the pressure. The good news is we don't deal with real gases here. When you do, it turns the ideal gas law into a scary looking gas law, which is known as the van der Waals gas wall, gas constant, and also gas law. And so the good news is you'll see that down the road, but not here. So everything we deal with is ideal situations. Non-ideal situations basically occur at really high pressures and really low temperatures. And the reason why you do have to take it into account at those situations is, if you remember from Boyle's law, if you have a really high pressure, you probably have a very small volume, which means all your gas molecules are pretty much right next to each other. And that means that they're going to definitely come in contact with each other. And also at a lower temperature, they're not going to be flying around as fast, which means they'll be in contact with each other for a much longer period of time. So under those sort of real conditions, you have to take that stuff into account. And also, if you think about it at the really small volume of the container, the gas molecule's volume is relatively significant compared to an ideal situation. So good news is ideal situation here, you don't have to worry about it, and you'll learn about real gases a little bit later on. So why don't you try one here? If we take 5 grams of helium and add 5 grams of neon to it at 27 degrees Celsius in a 2.5 liter container, what is the partial pressures of each gas, and also what is the total pressure. We're looking for three answers here, two partial pressures and a total pressure. Helium is 4.003, 2018 there for neon. Gas law again for each of them individually. We have grams of each of them, which we definitely could get to the moles. So we'll be able to get to moles for each of these. We also have a temperature that is 27 degrees Celsius. Like all gas laws, we'll convert that into Kelvin right off the bat. Why not? 300.15 Kelvin. We also have volume that's in liters, which is good. We always have R available to us. And at that point, really all we need to do is get some moles of each of these. So we'll go 5 grams of helium. We'll use the molar mass from the periodic table for helium, 4.003 grams per mole. That's going to get us here 1.249 moles of helium. We could do the exact same thing here for our other gas, our 5 grams of neon using the molar mass, 2018 grams per mole. Again, the grams are going to cancel here. That's going to get us here 5 divided by 2018. 0.24778 moles of neon. So to find the partial pressures, all we have to do is individually calculate it here. So P for helium would be nRT divided by V. So put in our numbers, 1.249 moles, 0.08206 liters atmosphere Kelvin mole. 300 here, 0.15 Kelvin, all divided by our volume of 2.50 liters. Liters are going to cancel, Kelvin cancels, moles cancel, leaves us atmospheres left over. And that's going to get us here 1.249 times 0.08206 times 300.15 divided by 2.5 and 12.3 atmospheres. And that would be our partial pressure of helium, basically, in this case. Any question on that calculation there? We're going to do the same thing here for our other gas. Nothing's really going to change here other than the moles. So we just want to make sure we use the correct moles. So we'll use our moles of neon, which is 0.24778. And again, because they're in the same container, in the same vessel, in the same room, everything here is going to be the same. So 0.08206 liters atmosphere Kelvin mole, 300.15 Kelvin, all divided by 2.5 liters. And that's going to give us a partial pressure of 2.44 atmospheres, would be our partial pressure here of neon in this case. At this point, we could get our total pressure by just simply adding those guys together. So our total pressure will equal the partial pressure of helium plus the partial pressure of neon. That's going to give us a 12.3 atmospheres plus a 2.44 atmospheres. That's going to give us a 14.7 atmospheres as our total pressure of this gas mixture. Any questions on any of that there? By the way, which one here is contributing the most to the pressure in this case? Which gas is contributing the most? It is helium, right, at 12.4 atmospheres. The reason for that is right here, actually. Helium is 4.003 grams per mole. Neon is 20.18. Because helium is a lighter gas, it has a higher root mean square velocity. It's flying around a lot faster. Since it's flying around a lot faster, it's probably causing more collisions. More collisions is why it's causing more pressure than the heavier neon that's moving a little bit slower in terms of its velocity, not causing as many collisions. Any questions on that there? So I would say this is a very common sort of partial pressure type of problem. Basically just an ideal gas law for however many gases you got together, and then you just add them at the end to get to your pressures. We are going to skip this mole fraction partial pressure. So we'll talk about another type here, which is this. So this is actually a lab we used to do. They got rid of it this semester, so you didn't do it. But we used to do this one. This is a decomposition reaction of potassium chlorate, and you would heat it up and make a little KCl and some oxygen gas in this case. And in this particular case here, maybe a 3, a 2, and a 2 there, maybe. You would actually start to heat it up, and this O2 had nowhere to go but in the tube, down through into this jar that's had water in it to receive it. And much like you did with the sort of tube when you did the magnesium experiment, water goes out, gas goes in, and you end up with this sort of empty spot. In the case here, the jar, or in your tube, you had an empty spot in the tube. It's really not empty. That is where the gas actually ends up, right, as it goes in there. And in the case of this experiment here, that was where your oxygen gas basically ended up. Now, whenever you collect a gas like you did in that experiment, or you do in this experiment here, where water's involved, there's usually some type of heat associated with it. And when you have heat and water together, you will also collect, in addition to the gas you're actually looking for, you'll actually collect some water vapor. And that water vapor is really just a byproduct of how you collected the gas. Is not anything you're interested in collecting or anything like that. So usually what we want to do in this situation is kind of get rid of the water's contribution. So what we actually have here is a partial pressure situation where the total pressure equals the pressure of the gas you're interested in plus the vapor pressure of water. And that is the vapor pressure of water, which is a chart that you could look up, which was on the whiteboard there in lab. And you look it up based on temperature. So most of the time in this situation, we use it as sort of a correction factor where you could take the pressure of the gas you're interested in, take the total pressure and minus the vapor pressure of water. The total pressure in the laboratory is your barometer reading, the atmospheric pressure. In the book type problems, they'll even give you the atmospheric pressure or tell you the total pressure, one of those type of words. This is also why sometimes this is referred to when you do this calculation and correct for the water, getting the pressure of the dry gas, right? You're removing basically water's contribution to it that you're really not interested in. Any questions on that there? By the way, this also goes for as well if you're given the total pressure and some partial pressures and want to figure out somebody else's partial pressure. You basically just subtract from the total pressure because all the partial pressure should add up to the total pressure. So for example, if there were 3 gases and you knew 2 of the 3 gases partial pressures and the total pressure of the mixture, all you have to do is subtract basically from the total pressure, and whatever's left over is the partial pressure of that missing gas there that you weren't sure of. So that's a very common sort of thing. Here's a table from your book again, much like the one that was hanging there. You want to look it up there based on temperature to get the vapor pressure of water. You do also want to always make sure, though, unit-wise, everybody is the same. So obviously, when you're adding or subtracting, they do need to be in the same unit of pressure. So I want you to try one here. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the oxygen gas? Okay, so there's a couple of words sometimes in book problems that you want to look for to know this is the situation going on. And that's a classic sort of verbiage there that you sometimes see in word and problems. If you see something that says it's saturated with water vapor, or sometimes they'll mention you collected it over water. Those are like the key words that you have this sort of situation occurring and that you have this sort of mixture happening here, pressure of your gas plus the pressure of the water vapor. In this case, we can find the pressure of the oxygen gas by taking, again, our total pressure minus the vapor pressure of water. Basically, these two guys switch. All right. And, or actually, you could just take this guy to the other side. And what we'll end up with in this case is our total pressure of 753 torr, which is usually our barometer reading. This again is a value that you can find on a table if it wasn't given to you. They are in the same unit, so that's good. That's going to give us about 721 torr. They do want it in atmospheres. So here again, we'll divide by the 760 to convert it into atmospheres. 0.949 atmospheres would be our pressure of our dry oxygen gas in this particular case. Any questions on that one there? So those are two common ways to sort of find partial pressures. Again, use the ideal gas law, or kind of like a subtraction type situation, which is not too bad. Any questions on that there? All right, to finish up here, we talked about some of these things along the way, the different parts of the kinetic molecular theory of gases. Let's just go over one more time here just to make sure. Gases consist obviously of tiny particles, atoms, or molecules. These particles are small compared to the distances between them, and that means that the volume of the individual gas molecules are assumed to be negligible or zero. That number two, again, is pretty much what makes something an ideal gas. That sort of second one there is one of the things that makes something an ideal gas. The particles are in constant random motion. Again, hitting the container, the collisions is what causes the pressure we associate with it. The particles are assumed not to be attracted or repelled by one another. That is, again, the second thing we talked about that basically makes something an ideal gas. And lastly, the energy associated with that's going on does affect the gas molecules. As the temperature increases, so does the energy of the gases, and they start to fly around a lot faster. So higher temperature, faster moving gas molecules could lead to higher collisions. Lower temperatures will slow down the gas molecules, could lead to less collisions. In a rigid container, if we open the temperature or increase the temperature, we're going to see the pressure start to increase because the volume is not going to adjust. That's our Guy-Lussac's relationship. Also, if we lower the temperature, we will see the pressure start to drop in that case. Charles' law, which is the bottom relationship that we talked about, again, it is that volume that adjusts to allow the pressure to remain constant. As we increase the temperature, because the gas molecules are moving around faster, the volume gets larger to keep the number of collisions basically the same and keep the pressure constant. And as we lower the temperature, the volume drops down smaller to keep the number of collisions basically the same and keep the pressure constant. So again, it's the volume adjustment